Okay, so here we are starting with Module 3 opened up. It's really just a simple outline on how to go through and simulate absorbance spectra with HITRAN. I won't go through all the text here. I'll let you work through that and read through that. But essentially, what we're doing is telling HITRAN which molecule isotope we want to look at, and then using that to download a data set. So we use the fetch function, and you can walk through all this in the HITRAN documentation, but this is kind of just an easy format to go through and convince yourself that you can run simulations. So let's just go through it step by step. Really what we're taking from the data set is the line positions, the line intensity, broadening parameters, and energy levels. So the HITRAN API makes it really easy. So install Happy, import some libraries. Okay. Then this is the setup of the database that gets saved locally. And it's kind of neat. I mean, HITRAN has a ton of molecules that you can download these line transition data for. I've explained it before. The file you download has a bunch of literal line-by-line data for every line transition that is included in the wave number range that you choose. It's also dictated by the isotope that you choose for that particular molecule. So here we're going to look at methane. So that's the molecule ID 6, isotope 1. And this is the wave number range of interest that we're looking at. I chose this just because it's it's 3 different major transitions. And so it gives us a really large methane range, concentration range to look at. And it's part of trying to understand how these machine learning models can help identify. Essentially, it's just going to be a voltage trace, right? So voltage versus time, and typically the signal from high absorbance environments really is not there, and so the idea is, can machine learning model identify how much what the mole fraction is from a given detector trace based on even though there's a lot of absorbance and a very low signal. So that's kind of what we're trying to explore. Okay. So then the data set gets downloaded for that particular molecule, wave number range, and then we can extract the information we need. So it's just it's how we use to be able to extract the data. So it's this dictionary, and then there's some details. You can print out some details on the. I commented this out because there's a ton of lines, but you can get details on what is contained within those data. It's just some notes here to read through. Essentially, the way we're modeling this is that because it's atmospheric, around 1 pressure, there's nothing, it's essentially the line shape is dictated by the Doppler broadening, which is temperature dependent. And then the collisions from molecules in the air and with itself. And so that's based on pressure broadening. And it's the convolution of that is the void profile. It's a great book. We call it within the folks, well, I don't know. I call it the spectroscopy Bible for gas spectroscopy, especially for these applications. Highly recommend having a copy of this spectroscopy and optical diagnostics for gases. Super helpful. But essentially, here's the definition, the Python definition that kind of uses these data, and here are the definitions of the parameters that we use. So let's go ahead and run that. And so here you can change these values to kind of generate a simulation. And here I've run that before, but here's the absorbance as a function of wave number. And so these are the 3 peaks that we'll be experimenting with. And here are the conditions. Just looking at standard 1 meter path length, 1% methane in air, essentially standard temperature in air. And you can use the following sections to kind of just play around with what happens if I change mole fraction. What happens what's the effect of temperature on all this? It changes a little bit, but temperature range has to be pretty wide, minus 20 to 50 C. And how does pressure affect this? Depending on what you're doing, it can be considerable. And then this is a neat class. It just allows you to be able to generate spectra kind of easily. And then this just allows you to save the data that you're generating. So I've used this particular file format so that in any given downloaded data set or simulated data that you've created, absorbance data, from the file name itself, you can identify what the temperature is, pressure, it just took a while to generate, path length, and mole fraction. This will be helpful for when we use the simulation to then start generating the data set that's used to train the machine learning model. So that'll get saved locally. And then you can use this part here to just kind of explore, again, different scenarios to calculate absorbance. Just provide some examples here, and then just a summary. And, this kind of establishes the assumptions that we're making for the simulations. And next, we're going to look at, okay, how do we translate these simulations into what the detector would see on any given sensor? So generalized sensor, laser hitting a detector. And we'll go to that next, which is what we'll use to start generating the training data set for the machine learning model. Here's just kind of some questions to think about. This module will hopefully, with future iterations, it'll change a little bit, but this is the basic idea. Essentially, here's the code that you would need to be able to simulate methane absorbance data. Thanks.